Hello, this is Professor Kuehn, and I'm going to solve the AP Physics problem of the air bubble originating from a deep sea diver. It says an air bubble originating from a deep sea diver has a radius of 5 millimeters at some particular depth h below the surface of the water. When the bubble reaches the surface of the water, it now has a radius of 7.0 millimeters. Assuming the temperature of the air in the bubble remains constant, we have to determine the depth h of the diver and the absolute pressure at this depth. Okay, so how are we going to solve this? Let's first of all draw this out, make sure we understand what's going on. So we've got this deep sea diver down here. Okay, so this is the deep sea diver. Okay, and the idea is that the deep sea diver blows out a bubble. I'm going to make this a little bit exaggerated, but the radius down at in the deep region is equal to, we're told, 5.0 millimeters. Okay, and then what happens is this bubble rises up to the top like this, and by the time it gets to the top, because presumably the hydrostatic pressure, the pressure with which the water around it is pushing on it, has gotten smaller just before it gets to the surface, the radius near the surface is around 7.0 millimeters, and this is right near the surface of the water. And by the way, you should keep in mind that at the surface of the water, the atmospheric pressure, the pressure at the surface, is right around 1 atmosphere. We're assuming that this is atmospheric pressure. Of course, that's because we're under an ocean of air, right? And of course, down here, there's going to be some pressure at this depth. Okay, now we're told that the bubble as it's rising retains a constant temperature, right? And so what that should make you think about is the ideal gas law, because that relates the pressure, the volume of the bubble, the air bubble, the number of moles of gas in the air bubble, the ideal gas constant, and the temperature, right? So these, presumably, the gas is going to obey the ideal gas law. So what we should recognize is that the temperature is remaining unchanging. The ideal gas constant, of course, is unchanging, and the number of moles of air in this bubble are also unchanging insofar as the air doesn't diffuse out of the bubble into the water. So we'll assume those are constant. So in other words, the product of the pressure and the volume are constant as the bubble rises. So that means the pressure in the deep region times the volume of the bubble in the deep region has to be equal to the pressure of the bubble when it gets to the surface multiplied the volume when it gets to the surface. And so you can probably see right away, we can relate the pressure in the deep region to the pressure at the surface if we know the relative volumes of the bubble at the surface to the volume of the bubble when it's very deep. Well, you know the ratio of the volumes for a sphere is 4/3 pi, the radius at the surface cubed, over 4/3 pi times the radius when it's very deep cubed. The 4/3 pi's go away, and so we can compare the radii of the bubble. So the radius at the surface is 7 compared to the radius down here is 5 millimeters, and we cube this. So 7/5 cubed, and that is, I did some calculations here, that's about 2.74. 2.74, okay? So the pressure in the deep region, the pressure in the deep region is going to be 2.74 times the pressure near the surface. That's an important thing to keep in mind. Okay, that's in fact why the bubble is compressed in the deep region. Okay, now we can do all kinds of conversions between pressure and depth, but I think it's probably good just to keep in mind a rule of thumb that 1 atmospheric pressure, 1 atmosphere corresponds to a depth of water of about 10 meters, which also corresponds to a depth of mercury around 760 millimeters or 76 centimeters. So 1 atmosphere is equivalent to 10 meters of water, okay? So if up here the pressure is 1 atmosphere and down here it's 2.74 times as much, that means that the pressure down here is about, the pressure in the deep is about 2.74 atmospheres, okay? So it's gone up by 1.7 atmospheres. okay? Which means that the depth of this, the height, if every 1 atmosphere corresponds to 10 meters of water, and the pressure has gone up from 1 atmosphere to 2.7 atmospheres, that means that the change in pressure is 1.74 atmospheres, which means the depth that it is about 17.4 meters. So that's a pretty easy way to figure out how deep the diver is, 17.4 meters, okay? And we've actually answered the second question. The absolute pressure at this depth would be 2.74 atmospheres. So that is the solution to that problem. If we wanted to convert to pascals, we could do that because there are about 100,000 pascals in 1 atmosphere, 101,000 pascals in an atmosphere, but we could do those conversions if we wanted to, but I don't really feel like doing that, and so I will stop there.